Worksheet on Atomic Physics, IGCSE Physics 0625, Paper 22, March 2021. Let me read. It says, one end of copper rod is heated. Okay, I'm so sorry. That's from thermal energy. But let's finish it. It's thermal physics. What is the one method by which thermal energy is transferred in the copper rod? Free electrons? Yes. Free electron transfer energy from the cooler end to the hotter end. No. Energy transfers from hotter to cooler. High energy to low energy. So that's wrong. Free electrons? Yes. Hotter to cooler? Yes. Next one. Molecules of copper move? No, they don't move. Molecules never move. They just stay in that place, tightly bonded. Alright, so that's B. Which change will cause a decrease in the rate of radiation emitted by object? Okay, changing the surface color from white to black? No, radiation will be more because it will have absorbed more energy. Changing the surface of texture from dull to shiny? Yes, energy will be absorbed less. Increasing the surface temperature? It will have more energy, so that's wrong. Increasing the surface area, more energy will be absorbed, so no. The answer is B. When alpha particles are incident on a thin metal foil, most of them pass through undeviated. What does this observation reveal about the nature of atom? The atom has dense nucleus? No, it doesn't affect that. The atom is mostly empty space. That's why it went pass through. Yes, correct. The atom is very small. Of course, atom is very small, but how does it matter? How does it affect that all the rays are passing through? The nucleus of the atom is positively charged. Then it should repel. So not that, not that, not that. A laboratory worker measures the count rate from radioactive source. He records his results in a table. At 0 minutes time and count rate. 0 minutes, 100 counts. 1 minute, 73 counts. 2 minutes, 54 counts. 3 minutes, 41 counts. 4 minutes, 31 counts. The average background radiation in the laboratory is 8 counts per second. What is the half-life of the source? Alright. The background radiation is 8 counts per second. And the worker has measured the count rate from the radioactive source, which is 0 seconds, 0 minutes, it's 100. 100 from the source plus 8 of the background radiation, it's 108. Half-life will divide 108 by 2. So that becomes 54. So my answer is 54 in 2 minutes. Fine, 2 minutes. Let's try next one. It's IGCSE Physics 0625, Paper 42, March 2021. State the proton number, nucleon number, and the value of the charge of an alpha particle. Proton number, okay, proton is 2 alpha 4 or 2 He 4. Nucleon number 2 plus 2, that's nucleon number, which is 2 proton, 2 neutron. So which is 2 plus 2, 4. Charge, since there are no electron, it's just proton. Charge of proton is plus 2 plus 1, so 2 proton plus 2. A nucleus of strontium-90 consists of 38 protons and 52 neutrons. Strontium-90 is radioactive and decays by beta emission to an isotope of yttrium. Symbol of strontium is Sr and the symbol of yttrium is Y. Write down nuclide equation for this decay. So first of all, strontium has 38 protons and 52 neutrons. So Sr, 38 and 90. They have given nucleon number is 90. In physics, we don't have to remember all that. It's chemistry that we have to remember How many protons, how many neutrons. Otherwise, we don't need for physics. It gives now beta emission. So beta emission is -1, beta 0. Now this is, since this is 38 and this is -1, the equation should balance, right? Yttrium is Y, 38 minus 1. So 38, so 39 minus 1 will give me 38, right? And 90 and 0, so that should be 90. 90, understand, 90 plus 90, 90 equals 90 plus 0, 90. And 38 equals 39 minus 1. The half-life of radon 220 is 56 seconds. A sample of radon 220 is in a container. After 112 seconds, mass of radon 220 is 9.2 milligrams. Calculate the mass of original sample. Now it says after 112 seconds. So 56. So first, let's understand like this. Time is, for example, 0 seconds. From there, it becomes 56 seconds. So one half-life is elapsed. Then again, another 56 seconds, 112 seconds. So how many half-life elapse? 2 half-lives elapse. That means if here I have some amount, divide by 2 is that amount, and divide by 2 is that amount, and that at the end I have 9.2. So if I'm going backwards, I will multiply by 2. 9.2 is 18.4, multiply by 2, and that is again 36.8, approximately 37. 4 students are asked to comment on process of nuclear fission and nuclear fusion. Which comments are their comments are recorded in the table. Which row is correct? Now, if we remember, for nuclear fission and nuclear fusion, it says the nucleus becomes highly unstable and splits into 2 large lighter nuclei, that is shooting 2 or more neutrons, that is fission. It's on page 260, which means in nuclear fission, highly unstable nuclei splits into lighter and stable nuclei, right? So that's fission. Okay, that's correct, right? Energy, then in that energy is released. Energy is released. It says, and so on. The result is a chain reaction and a huge rapid release of energy. So energy is released. Not this, not energy is absorbed and 2 light nucleus joins. Light nucleus joins is fusion. Now fusion is on next page. It is on page 262. It says, check page 62. Okay. Protons and neutrons in middleweight nuclei tend to most tightly held, so splitting very heavy nucleus releases energy. That happens in nuclear fission. However, energy can also be released by fusion, which is joining very light nuclei together to make heavier one. This is called nuclear fusion. So, large nucleus splits? No. Energy is absorbed. Okay. Energy is absorbed or released? Tell me. Okay, the energy is released, right? Not absorbed. Energy is absorbed? No. And 2 light nucleus join? Yes. So which one is correct? D. 39. Radon 86, radon 219 decays by emitting alpha particles. What nuclide is formed in this decay? Okay, alpha particles. So let's try this. Okay, 86 Rn 219. Alpha particle is something, I don't know which particle, but alpha particle is 2 protons and 4 nucleons. So 86 minus 2 is 84, and 219 minus 4 is 215. So let's check which one is that. This is that polonium. So that's polonium, right? Let's try next one. The graph shows the activity of a radioactive source over a period of time. What is the half-life of the source? The half-life of the source, okay? It says 120, and 120 minus divided by 60, which is divided by 2 is 60. So at 2 minutes we have 60 counts per second. So half-life is 2 minutes. Next one, IGCSE Physics 0625, paper 41, June 2021. There are 3 naturally occurring isotopes of hydrogen: hydrogen 1, hydrogen 2, hydrogen 3. The nuclide notation for hydrogen 1 is 1H1. Write down the symbol using nuclide notation for hydrogen 2 and hydrogen 3. So hydrogen 2, it is 1 proton, that's why hydrogen is on the first place in periodic table. Hydrogen 2, that means there are 2 nucleons. Again 1 proton, symbol is H, and 3 nucleons. Number B, in a fusion reactor, a nucleus of hydrogen 2 and nucleus of hydrogen 3 undergo fusion. State what is meant by nuclear fusion. Nuclear fusion means small atoms joined to small nuclei joined together, right? That's what we did. We read just now what it was on page 262. Okay, it says however, energy can also be released by fusion, joining very light nuclei together to make heavier ones. This is called nuclear fusion. So this is nuclear fusion. We can say joining together of nuclei to produce a bigger nucleus which is helium nucleus, or alpha, we can say even alpha, okay, He nucleus with release of energy. Let's try the next one. Now it says the fusion reaction produces a free neutron and one other particle. Write down using nuclide notation the equation that represents this reaction. All right, so that's 1H2 because it's hydrogen 2 and hydrogen 3 plus 1H3. They undergo the it says fusion, right? Fusion, they undergo nuclear fusion. So it is 1 plus 1, it is 2, alpha 4, the alpha particles are formed, right? Then if you notice, that's 1 plus 1, 2, done. Plus something is created. We'll see what is created. Then next is 2 and 3, 5, but here it is just 1. So that's 1 and 0. So 1 and 0 is what? Neutron, right? It even tells us that the fusion reaction produces a free neutron. So that's free neutron. And one other particle. That other particle is alpha particle. All right. Number C now. It says Nuclear fusion in the sun is the source of most but not all of the resources that are used to generate electrical energy on Earth. State two resources for which nuclear fusion in the sun is not the source. So nuclear, it's geothermal energy, right? Geothermal energy. Then the other one is tidal energy, tides, right? And third is nuclear energy. Now, IGCSE Physics 0625, paper 22, June 2021. Which row correctly states how nuclear behave during nuclear fission and during nuclear fusion? I'm so sorry. Which row correctly states which nuclei behave during nuclear fusion and fission? All right, so first is fission, second is fusion. In fission, heavier nucleus splits, right? So join together, no, split, yes. In fusion, they join, lighter nucleus join, yes, split, no, join, yes, split, no. So which one is both correct? C. Let's try number 38. The charge on a proton is E. What is the charge on electron? What is the charge on a neutron? All right, let's try that. If we say charge of proton is +1. Now they are saying charge of proton is E. Which means if I say charge of proton is +1, charge of electron is -1. Which means it is the negative charge of the whatever is given. So if the proton is E, electron will be negative E. So negative E, right? Neutron, we know neutron does not have any charge. So it's 0, 0. So that's D. 39. Some radioactive nuclei decay to give new nuclei which are also radioactive. Part of the series of decay is shown. 92 uranium 238 gives thorium 90-234. From there we get Pa 91-234, U 92, uranium 92-234, thorium 90-230, and radium 88-26. How many decays involve the emission of beta particle? Let's try this. All right. So, in beta decay, one neutron changes into proton. So, the proton number, atomic number, increases by 1. Right? They have asked about how many involves emission of beta particles. So, we need to check where the atomic number increases by 1. No. Increases by 1? Yes. By 1? Yes. No. This is alpha radiation, right? Alpha. This is alpha. All right. Because in alpha radiation, the proton number, which is atomic number, decreases by 2. In beta radiation, proton number, which is atomic number, increase by 1. So that's 1 and 2. The graph shows the activity of a radioactive source over a period of time. What is the half-life of the source? All right. Half-life of the source. So now let's draw. From 120, I draw at 60. There is no mention of background radiation. So I will take it completely as 120. So that's 2 minutes. Two identical radioactive sources emit alpha particles and gamma rays into 2 vacuum tubes. Figure 8.1 shows 2 electrically charged plates on either side of one of the vacuum tubes. So if you notice the plate, this is positive and this is negative charge. Sorry. Okay, initial path of alpha particles and gamma rays, source, vacuum. Write the symbol alpha once in table 8.1 to indicate any deflection of the alpha particles. Okay, let's try that. Deflection of alpha particles. So alpha particles are positive, so they will deflect towards the negative plate, right? They will deflect towards the negative plate, all right? So they go towards bottom of the page. That's alpha particle. All right. Let's try the next one. Write the symbol gamma once in table 8.1 to indicate any deflection of gamma rays. Gamma rays have no charge, so they will go straight. They will pass straight through that. So it is no deflection. That's gamma rays. If there was beta, if there were beta rays, then beta rays will be bending the, but remember alpha rays bend less, beta rays deflect more. So you should always draw the path of beta rays more longer compared to the alpha rays. But that's not the question, so let's forget about that. All right. Figure shows poles of very strong magnet on either side of the vacuum tube. Okay, north pole, south pole, vacuum, source, initial path of alpha and gamma. Write symbol alpha once in the table to indicate any deflection on alpha particles. Write symbol gamma. Okay, let's try first alpha. So alpha is positive, right? So it will bend towards negative. So alpha will go into the page because south pole is negative, north pole behaves as positive. So into the page, alpha is into the page. So south is negative, remember, north is positive. That's negative and this is positive. All right, next one. The symbol gamma once in to indicate deflection of gamma rays don't deflect. They don't have any charge. So they go straight. No deflection. That's gamma rays. A student investigates a radioactive substance in a laboratory. Figure 11.1 is a graph showing the count rate detected as substance decays for 7.5 minutes. The background radiation is 20 counts per minute, right? So we say that determine the half-life of the substance. All right, let's try this. Now 220, it says the graph showing count rate detected, right? 220 was count rate at the beginning, right? And the background radiation is 20. That's 240. So 240, half-life is 2 divided by 2 is 120. So from 120, draw a line reaching the graph. From there, reach down and check where do you end. Sorry. That's 2.4 minutes. Calculate the count rate detected at time 9.6 seconds, right? 9.6 seconds. So that was 200 because 20 is the radiation, right? So background radiation. So I'm trying like this. 220 minus 20 is 200. So 200 divided by 2 is 100, right? The first half-life, because the half-life is, it says, sorry, half-life is, we have calculated 2.4 minutes, right? So 9.6 divided by 2.4 is 4. So we need to divide 4 times. 50. So that's one time. Second time. Third time is 25. Divided by 2. Fourth time is 12.5. So either we can take 12 or we can take 13, right? But remember, there was background radiation of 20 counts, right? We have background radiation of 20 counts. So the reading will be 13 plus 2, 20, which is 33, or 13, 12 plus 20 is 32. So 32 or 33 counts per minute, whatever you feel better. The substance emits alpha particles and gamma rays. The student suggests that it is safe to store the substance in plastic container of thickness 2 mm. State and explain whether the student's suggestion is correct. Right? So it's incorrect. What does it say? He says the substance emits alpha particle and gamma rays. He says that it is safe to store substance in plastic container of thickness 2 mm. Okay, alpha particles can be blocked by paper also, thick sheet of paper also. But gamma rays, even with lead, it's difficult. It's not 100% safe. So we can say container does not absorb or stop. Container won't block gamma particles. Right? So 3 marks, as it's partially incorrect. Gamma is dangerous. Gamma rays are dangerous and will need thick lead to stop gamma rays. Still no guarantee. IGCSE Physics 0625, paper 23, 2021. The change on proton is E. Now, let's try this. All right. The charge on proton is E. What is the charge on electron? And what is the charge of neutron? Proton is E, so electron is negative E, and neutron is 0. That's D. The diagram shows alpha particles incident on a thin metal foil. How does the motion of the particle or this particle give evidence for the nuclear atom? Right? So we have to see the options. The options are missing. The diagram shows alpha particles incident on a thin metal foil. How does the motion of these particles give evidence for the nuclear atom? Okay, let's try this. It says evidence for the nuclear atom. All right. Most particles passing through with minimal deflection. Let's try. Yes. Minimal deflection. Yes. Most particles. Only 1, 2, and 3 and 4 are deflected. All right. This is actually reflected. So 3 deflected, 1 reflected. Most particles passing through with minimal deflection shows that the mass. Okay, sorry, I didn't read the completely. I'm sorry. Minimal deflection shows that the atom is mostly empty space. Yes, Rutherford Bohr model, remember? Most particles passing through with minimal deflection shows that the mass of the atom is uniformly distributed. No, because mass of the atom is in the nucleus only. That's what it shows. Large deflection of some particles show that the atom is mostly empty space. Okay. If there is large deflection, then it won't show the atom is mostly empty space. The rays should pass through that. And number B is not that, because mass of the atom is uniformly distributed, doesn't relate with deflection, not deflection. But we know that most of the mass is in nucleus. Large deflection of some particles show that charge in atom is uniformly distributed. Now, that was Bohr model. Remember? Plum pudding model. So that's number A. All right, let's try the next one. Number 39. Radium 226, 88 radium 226 is an alpha emitter. It is implanted inside cancerous tumors. It is safe to use it as it kills the cancerous cells, but not the healthy ones surrounding the tumor. Which properties of alpha particles compared to other emissions enable this use of radium 226? This question says that we are implanting, using chemotherapy maybe, we are implanting alpha particles in the cancerous cells. So it kills the cancerous cells but not the healthy cells around it. What property is we are using here? Okay, ionizing effect of alpha particles. It's high. Yes, we know ionization is high for alpha particles. And then penetration of alpha particle is low. It can be stopped by skin also, it can be stopped by the paper also, so penetration is low, right? So which means that we can direct it to the cancerous cells and it will be stopped there. So which is correct for both? It's B. Number 40. The graph shows activity of a radioactive source over a period of time. What is the half-life of the source? All right, half-life 120 we have. So from half of 120 is 60. From 60 we draw a line, go down. That's 2 minutes. That's my answer. Right? Now, figure shows beam of radiation in a vacuum. The beam contains alpha particles, beta particles and gamma rays. Okay, so that it says it's the beam of radiation, region of uniform magnetic field out of the page, right? Then the question says the beam enters the region where there is strong uniform magnetic field. The direction of the magnetic field is out of the page. Out of the page is top of the page. That's out of the page. That's into the page, right? So when they say out of the page, that means going top, on the top, and in the page is coming down. All right. The direction of the magnetic field is out of the page. Okay. On 10.1, mark the label the path through the magnetic field of number 1 alpha particle. Label this path as alpha. So magnetic field is, it says out of the particle. That means that is positive and that's negative. Number 38, it says, the diagram shows alpha particles incident on a thin metal foil. How does the motion of these particles give evidence for the nuclear atom? All right. So if we notice, the most of the rays are going undeflected, passing undeflected through thin metal foil. It tells us most of the atom is empty space. Only few like this are deflected a little, right? But this one is reflected. So, all right. Which means if the atom is like that, it's Rutherford Bohr model. Remember, we had discussed. So that's the nucleus. Nucleus has proton and electron. Proton and neutron. Electrons are outside. So when any rays is passing through, so it is passing through, it goes undeflected. But if it tries to go closer, it bends. If it goes like this, directed, reflected, bends, passes through. It's like that. So that's what this is showing. All right. Most particles pass through minimal deflection, shows that atom is mostly empty space. Yes. Most particles passing through with minimal deflection shows that mass of the atom it doesn't relate with the mass of the atom uniformly distributed. Large deflections of some particles show that atom is mostly empty space. If it was empty space, it would pass through. So large deflection shows they are going towards the nucleus. So not that. Large deflections of some particles show that the charge in the atom is uniformly distributed. No, it doesn't show about anything about charge. Charge is uniformly distributed. It will show the same deflection for everything. All right, so that's number A. Radium-226. 88 radium-226 is an alpha emitter. It is implanted inside cancerous tumors. It is safe to use it as it kills the cancerous cells but not the healthy ones surrounding the tumors. Which properties of alpha particles compared to other emissions enable this use of radium-226? So when you concentrate radium through chemotherapy to cancerous cells, they penetrate the cancerous cells, right? And they kill cancerous cells. Then they cannot penetrate the healthy cells around it because they can be stopped very easily. So let's see ionizing effect. It has high ionizing effect to kill them. And not low. And penetration of alpha particles are low. So that's why they are stopped. Right? So that's both correct. That's B. That's why they are stopped and not killing healthy cells. Number 40. The graph shows activity of a radioactive source over a period of time. What is the half-life of the source? If you notice, there are 120 counts per second. So half of 120 is 60. So from 60, draw a line and check in what time you get 60 counts per second. That's 2. So the answer is 2. Let's try. IGCSE Physics 0625, paper 43, June 2021. Figure shows beam of radiation in a vacuum. The beam contains alpha particles, beta particles, and gamma rays. Beam of radiation is passing through the, right? And region of uniform magnetic field out of the page. When it says uniform magnetic field out of the page, that means out of the page is north. In the page is south. So south is negatively charged. We consider north to be positively charged because that's where the rays bend. Now, the beam enters region where there is a strong uniform magnetic force. The direction of the magnetic field is out of the page. On figure 10.1, mark and label the paths through the magnetic field of alpha particles. Now, alpha particles are positively charged, so they will bend towards southern pole, because southern pole is negatively charged. Beta particles will go towards north pole, but remember it will go bit further than alpha particles, right? Because they can penetrate more. Gamma rays will goes undeflected because they don't have any positive or negative charge. Number B. Radioactive sources have many uses in medicine. State 2 safety precautions which hospital staff take when working with X-rays. Gamma ray source, not X-rays, gamma ray sources. So they should stay behind the shielding. You must have seen the technician who takes X-rays. he has special room. He doesn't stay with the patient in the same room. So stay behind shielding. Shielding provided, or walls you can say, as far as possible. As far as possible. Number 2, the store, gamma rays should be stored in lead lined boxes. Number 3, the exposure time should be limited, right? Exposure time should be limited. Then number 4, we can see no pregnant women allowed. No pregnant women or staff allowed. Number C, the radioactive isotope iodine 131 is used as a tracer in medical diagnosis. A nucleus of iodine 131 contains 53 protons, 78 neutrons. The symbol of iodine is I. Use nuclide notation to show this isotope of iodine. Okay, it says proton 53 plus neutron 78. 78 plus 53, 8 plus 3, 11, carry over 1. 12 and 1, 31. Okay, it says iodine 131, correct. So I, proton number is 53. So atomic number 53, mass number 131. That's nuclide notation. Iodine 131 emits gamma radiation. It has a half-life of 8 hours. Explain why this emission and this half-life makes iodine 131 suitable material for a tracer in medical diagnosis. Now, medical diagnosis should have something that gives us clear picture of inside first thing, right? And then it should, the effect of it should wear off quickly. So half-life should be less, let's say. Okay, so what do we say? We can say gamma rays are can be detected outside the body. Detected outside the body. Number 2. So half-life is long enough to reach the part. Half-life long enough to reach the part. Short enough, half-life is short enough to wear off the, okay, let's write not wear off, we can say to have lethal activity. Okay, lethal activity inside the body. Number 4, they are weakly ionizing, so ionizing effect is less. Effect very weak, so does not harm body much, or very little harm, we can say. Not that we can't say they don't harm the body, they do harm the body. Number 37. IGCSE Physics 0625 21 November 2021. The nucleus of an americium atom contains 146 neutrons, 95 protons. It decays by emitting alpha particle. How many neutrons and how many protons remain in the nucleus when this atom, when this form of americium decays. All right, so let's try that. First of all, we have 146 neutron, so 146 plus proton is 95. So 11 carry over 1, 14 carry over 1, 241. So we have, okay, so americium is, I don't know, we can write protons, let's say it's A, right? And then it is 95 and 241, right? So this gives, let's say it turns into B. So 95 minus 2, that's 93, and 241 minus 4, that's 237, plus alpha particle is alpha 2 alpha 4. So proton, which are 95 minus 2 becomes 93, and neutron, proton, this is proton plus neutron. So neutron is 241 minus 2 is, sorry, not 241, neutrons are 146. 146 minus 2 is 144. So that's proton, that's neutron. 144 and 93, so that's C. The graph shows how the count rate measured by a radioactive detector placed near a radioactive sample changed with time. All right. We are given a graph. Given that background count rate is 30 counts per minute, what is the half-life of this sample? All right, let's try this. So first of all, we have to check background radiation is 30. So that's 30, right? All right. So we try, how much was that at the beginning? 500, 5, 10, 520, 530. So 530 minus 30, that's 500, right? 500 divided by 2 is, I'm removing background radiation because background radiation, they said it's 30 counts per minute. So 250. All right. Next it says, so 250. 520 minus, so 250, 2.4. So that's 250, right? 2.5, not 2.4. All right. So that's 530 to begin with minus 250, half-life, 0, right? So that's 380. No, 280, sorry. 280. So from 280, I draw a line reaching that. From there, I draw a line reaching there. What's that? 3.4. 3.4 hours. So half-life is 3.4 hours. So understand what I have done. What did I do? The background radiation, they said, was 30 counts per minute, right? So I subtracted from 530 minus 30. So I got 500. Then I tried what is half of 500, because actual radiation coming through the source is 500. So I got 250. But my reading starts at 530. So 530 minus 250 is 280. So from 280, I draw a line reaching the graph and I land down and I read what time it is. That time is 3.4 hours. So that's my answer. Let's try 39. A teacher holds radioactive source near a detector. The reading on the detector is 320 counts per minute. The detector is switched on again after the source has been removed and it shows a reading of 20 counts per minute. What is the counts per minute solely due to the source, and why is there a reading on detector when there is no radioactive source present? Now it says there is a radioactive source near a detector. The reading is 320 counts per minute. The detector is switched on and after the source has been removed. So first we have a detector, we have a source, then the detector is switched on after the source has been removed. And then after removing also, it is still showing some reading on that. What is the counts? So counts per minute solely due to the source, and what is the why is there a reading on the detector when there is no radioactive source present? When source and detector both are in, it was 320, right? The reading after the source being removed is 20. So minus 20. So 300 was due to the source and 20 is due to the background radiation. Counts per minute due to the source is 300. Right? Reason for reading with no source. Why there is reading but there is no source? Still there is a reading. Zero error on the detector, no. Background radiation, yes. Zero error on the detector, no. Background radiation. So answer is A. Now try 40. Now it says, which statement is not correct? A. Alpha particles are used to detect cracks in metallic sources. No, those are gamma particles. Beta particles are used in the measurements of the thickness of the paper. True. Gamma rays may be used to treat cancer patients. Yes, true. Smoke alarms contain a weak source of alpha particle. Yes. So what's the answer? A. IGCSE Physics 0625, paper 22, November 2021. The nucleus of an americium atom contains 146. This we have done just now. Let's try number 38. And the answer was C. We have done this. Here. This is the question. All right. A sample of americium decays and changes into neptunium. The half-life of americium is 432 years. Which fraction of the americium will remain after 1728 years? All right. Let's try. So from 0 to 432 years, half of the sample will remain, correct? Because half-life is 432 years. Then from 432 to 432 times 2, so that's 864. Another half will decay. So now the quarter sample remains, right? Now 864 to 432 times 3, so that's 6, 9 and 12, 1296. So that is 8 sample. Let's try this. It was, what years? 432. 432 times 3. So that's 6, 9, 12. And 432 times 4 is 8, 2, 1728. Alright. So 1296 to 1728. Half of 1 over 8. So how much remains? 1 over 16. Half-life means first half-life, for example, the half-life is 5 minutes and I have 50 counts. Okay, let's start with 100. It's easier. Let's say half-life is 5 minutes and I have 100 count radiations. So 100 counts of radiation in half-life. So after 5 minutes, out of 100, only 15 can be detected. 15 rays can be detected. So I have 15 counts reading. Next 5 minutes, because again the half-life is 5 minutes. So next 5 minutes, so it's in 10 minutes. Half of 50, 25. Next 5 minutes, so 15 minutes, half of 15, 7.5. about 8 radiations. Then again half of that. So half of 8, 4. So I have 4 counts per. I can have 4 counts radiation detected on my meter. Alright, so that's 1 over 16. So answer is 1 over 16. Alright, let's try the next one. The graph shows the graph shows the decay curves of the 4 different radioactive isotopes. Which isotope has the largest half-life? Now if you notice, let's see this. This one is decaying faster, so small half-life. This is still larger than this one, so larger half-life than D. C is decays even less in given time, so larger than C. And A is nearly intact, so it has the longest half-life. So A, my answer is A. The diagram shows alpha particles and beta particles passing through an electric field. The diagram shows correct path of, which diagram shows the correct path of the alpha particles and beta particles. Okay. Now, A, alpha is bending, beta is bending. Okay, B is also bending. C, beta is bending towards negative, so not, definitely not. Alpha bending towards, deflecting towards positive, not. D again shows alpha towards positive, beta towards, so out of A and B. Now we know that beta has more ionizing if alpha are more ionizing, right? More ionizing effect. But they are not so strong, but beta are more stronger. So beta bends more, but alpha, since they are far away from the plate, negative, they bend towards positive side. But since they are far away from positive side, positive plate, they go a bit straighter and then deflects little. So my answer is B. Here this one shows they both deflect at the same rate, which is not true. Alpha deflect less, beta deflect more. Alright. Describe the composition and structure of a neutral atom of beryllium 8, which has a proton number of 4, nucleon number of 8. So let's try this. It says nuclear structure of beryllium 8. Very small nucleus. Nuclear structure is very small nucleus and surrounded by electrons in orbit or shells, neutrons and protons in nucleus, neutrons and protons in nucleus. Okay, beryllium 8, right, has 4 protons, right? So it's 4 Be8, correct? So it has 4 protons, so it has 4 electrons. So 4 electrons and 4 neutrons in nucleus. All right, let's try. If it is 4 marks, remember you have to write at least 4 things. Number B now. A radioactive isotope decays by beta emission to form an isotope of barium with nucleon number 135. Alright. Element iodine, xenon, cesium, barium, lanthanum, cerium, and dash 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 dash, right? Symbols are given, proton numbers are given. Use data from table 11.1 to write down nuclide equation for this decay, right? So radioactive isotope decays by beta emission from an isotope of barium, right? So it is to form barium atom. So barium atom is formed. So it's barium. Now barium has 56 protons. 56 protons, and it says, okay, nucleon number is 135. So 135. All right, and it forms barium used by beta decay. So that's beta decay is 1 electron. So -1, beta 0. We have to remember that it is coming through from cesium. So Cs, right? Now 56 minus 1 is 55, right? Why I said we have to remember it is coming from cesium? Because 56 minus 1 is 55, and check, 55 is for cesium. That's why I said remember it's coming from cesium. And nucleon number is unchanged because 0 plus 135 is 135. Now IGCSE Physics 0625, paper 23, November 2021. The nucleus of americium atom contains 146 neutrons, 95 protons. It decays by emitting alpha particle. How many neutrons and how many protons remain in the nucleus when this form of americium decay? Now americium atom decays by emitting alpha particle, right? This we have done. We have done this already. This question is repeating again and again. The half-life of lead-202 is 52,500. A sample of lead-202 produces 800 counts per second. How long will it take for the count rate to drop to 100 counts? Alright, so it is 800 counts per second. 800. So divide by 2 will be 400. Divide by 2 will be 200. Divide by 2 will be 100. So this is first half-life, second half-life, third half-life. In 3 half-lives, it will reduce to 100. Now it says half-life is 52,500. So 52,500 times 3, because 3 half-lives, 0, 0, 5, carry over 1, 6 and 1, 7, 5 times 3, 15, 157,500. So that's B. Let's try the next one. Now it says oxygen 15 is used in hospitals. The count rate from a detector placed close to a sample of oxygen 15 was recorded over a period of 15 minutes. The background count rate is 20 counts per minute. What is the half-life of the sample of oxygen 15? All right, let's try this. It says oxygen 15 is used in hospital, right? Count rate from the detector placed close to a sample of oxygen 15 was recorded over a period of 15 minutes. So in the beginning it was 180, right? So now the background radiation is 20. So 180 minus 20 is 160. 160 divided by 2 is 80. But we have to start with 180 because background radiation plus the radiation from the source is what the meter will pick. So 180 minus 80, because that's what the reading was, but the half-life is 80 only. We consider the half-life for the source only, because background radiation always remain. So 180 minus 80, 100. Again, let's understand. The reading was 180. The background radiation is 20 counts. So 180 minus 20 is 160. So 160 counts are from the source only. right? And we have to consider the half-life of the source, not the background radiation. That's why I don't do 180 divide by 2, which is 90. I try 160 divide by 2, because 160 are the counts from the source. So 160 divided by 2 is 80. So 80 is the half-life for the source. But the meter picks up background plus source. So meter will pick 180. So 180, from 180 I have to subtract 80. So that's 100. From 100 I draw a line going there, and then I measure, what's that? Sorry. So that's 2 minutes, right? So that's 2 minutes. It is there. All right. Of the 3 types of ionizing radiations, alpha, beta, gamma, why does alpha emission cause the most ionization? Alpha particles have smallest mass. No, that's the helium. Alpha particle is Al2, alpha 4. Beta particle is -1. Beta, which is electron 0, less. This is 1800 times 2, right? Times 4 in fact, because 2 are proton and 2 neutron. And this is just small, very little, negligible. And gamma is just a electromagnetic radiation. Alpha particles have greatest mass, yes. Alpha particle move with greatest speed, no, that's no. Alpha travels to the greatest distance in matter, no. Most ionization is due to greatest mass. Alright, IGCSE Physics 0625, paper 43, November 2021. A detector of radioactivity is placed in a laboratory where there are no radioactive samples. A student notices that the detector shows the count rate that varies between 20 and 24. Suggest a source that of this reading. Okay, there is nothing, there is no source, but there is background radiation. So background radiation, this is, the reading is because of background radiation. Or you can say cosmic rays, or sun, space, star, building materials, earth, rocks, anything. Radon gas, humans, animals, right? Explain why these readings are not constant. Because radioactive decay is a random process. Radioactive decay is a random process. What does it mean? We cannot detect when will that radioactive substance disintegrate, right? We cannot predict the time. So that's why it can be any time. So that's the random process. A nucleus of uranium contains 92 protons, 146 neutrons. It decays by emitting alpha particle to become a nucleus of thorium. Complete the nuclide equation for this radioactive decay. Alright. Now, nucleus of uranium contains 92 protons. So I write 92. And 146 neutrons. So 146 plus 92 is 8. 3, 238. So I write 238. Now it is decaying by emitting alpha particles. Alpha particles is 2 protons, 2 neutrons, 2 alpha, 4. 92 minus 2 is 90, and 238 minus 4 is 234. So it's 90 thorium 234. An isotope of radon has half-life of 3.8 days. It decays by emitting alpha radiation. Calculate the time taken for 16 mg of this isotope to decay 2 mg of this isotope. Okay, 16 divided by 2 is 8. So that's first half-life. Divide by 2 is 4. That's second. Right? 4 divided by 2 is third, which is 2 mg. So that's what was, how many half-lives do you need? 3 half-lives. What was the half-life? 3.8 days. So 3.8 times 3. 8 times 3, 24, carry over 2 point, and 3 times 3, 9, plus 1, 10. Okay, plus 2, it's 11, 11.4, so approximately 11 days. Hope you understood everything. If you have any query, please contact me.